So today we will continue our work with factorial measures, and we will see some multivariate form of Mecke equation. So we saw it in one-dimensional form, and today, since we know how to produce a product of measures, we will see multivariate form of such equation. Okay, so let's continue. So let me remind what we did on previous lecture. So we defined so-called factorial measures or factorial a product of a point process. So since we consider a point process as a random measure, we defined a factorial measures of it. So let me recall how it looks like. So I start with a simple form of the point process that can be represented as sum of delta measures at some random points. So assume we have some number of them, and this is a point process. So here we can consider this x as a random variables in some space. And we defined and we defined a factorial measures of this random measure eta as follows. So we defined them on product of the space x m. So let it be m factorial measure. So we take subsets from sigma field of m's power of initial one, and we define for this kind of point process m's factorial as sum over all non-equal indices. So we consider only non-equal, and here delta measures at this random vector with here maybe x capital, xi first, xi2, and so on, xim. So on the picture, we saw that we consider only those points. So if I have case m is equal to 2, and I have here some random points, then I consider all except diagonals. So here, like usual product of two measures, but now we consider only this one, okay. So this notation we can write as, so if I have some subset C in Xm, so we can consider the action of this measure on this set. So this will be just a number of points that belongs to this xi first and so on. So we have random vector belongs to this set C, and again summation is over all non-equal indices. So here maybe you should know that if in our initial point process we have less points, so we know that if I have eta of the form, okay, if I have only two summands x1 plus x2 like this, then what will be my third power? Actually, this is 0, since we do not have such number of, so this is equal to 0, because this we do not have, does not exist, 3 non-equal indices in subset of indices of the points. So this means that the factorial power of measure is 0 if we have less points than we consider this power. So, and since we write this equality for measures, we can define the action for integral with respect to factorial measure. So if I have a function f that acts from xm to r, then what is the integral of a function f? Let me write here y eta m dy. So from our definition, this is just summation. Again, if I have measure mu of this form 1, 2, and 3. Then I have summation over all non-equal indices m f from x I1 and so on x I m. So this is just for recalling. And here we define this factorial measures just for point processes of this form, but we can easily generalize this definition, since we can write down recursive formula for power m and so on. So how it can look like. So we did not write it before. Recursive formula for e to the power m. So first one eta. First we define just as eta by itself, because this is just if we want to define this factorial measures of such form, we can see that this is just summation over one index, and this is the measure itself. And from this, let us write this form, and using this one, we will see what kind of recursive equation we can get for factorials measure itself. Okay, so next one, if I have eta m plus 1. So if I have just this is like intuition for eta of such form, delta xi to m, we recall that we have this delta xi first and so on, xims for non-equal indices. How then I can write the measure m plus 1? So this will be a summation of m plus 1 non-equal indices, xa m plus 1. Now I want to split the last one m plus 1 indices index and write like summation over im indices. And here, what do I have? I have that here summation over im plus first. That is just arbitrary. The xi1 xim plus 1 minus, so I add all of them, so I need to subtract those who which is equal to this one, so from the previous subset xi1 so xim plus 1. So with this in mind, we this what I copied. So with this in mind, we can write the equation for itself. This was just from the definition for such form of measures, but we can write the factorial measure itself. So I just write this definition in terms of integrals. So integral here, let me write the measure the factorial power m plus 1 from some subset C. So this is equal the integral, so this corresponds to this one. Then I open brackets, and here I write the integral over indicator that x1 and so on, xm plus 1, such a vector belongs to C. So since this summation over one index, this means that here in the integral I will integrate over one-dimensional measure dxm plus 1, just with respect to the last index. So here we can write over x. And then minus. This minus will correspond to this part. And here I have summation. So I will sum over all possible values of the last point, so of the last index. So they can be all previous values. So here I write summation over indicator x1 so xm, and here x yod. Yod is from 1 to m. So this last point can be one of the previous one. And this vector belongs to C. So I just write down this summation without the integral. And now I close the bracket and I write this integral with respect to factorial power of order m dx1 dxm. So this integral over space x to the power m. So here you can see that we obtain the recursive formula for a sequence of measures, and this formula is true for such measures of form delta of a finite number or delta measures at random points. So we can use this definition just to define the factorial power of any kind of random measure, not only of the form of sum of delta measures. So this is the addition for the definition of the factorial measures. So now I suppose we understand how we define the factorial measure for arbitrary measure. So let's come back to the end of our lecture, and I want to recall that we we wanted to consider some assumptions that will guarantee that if we know that factorial measures are equal for 2-point processes, so we want to know if the point processes itself are equal by distribution. So what will be done? So at first, let us let me recall the definition of factorial moment measures. So factorial moment. That was an analog of measure of intensity of a point process. So if I write the expectation of factorial moment of the point process, some subset D, C, then this is by the definition will be some, so this is some measure on product is a measure on the product of the space of the power m, and we call this measure is factorial moment measure. So, and we stop on the statement that says under what condition on factorial moment measures we will have uniqueness by the distribution of the point process. So what we did previous time, we proved the following formula. We proved, I just want to recall, we proved the following formula. So we take for some for a set B in this sigma algebra X, we assume that there is some non-negative constant such that n factorials measure of b to the power n, so this is usual Descartes product of subset B, is bounded by the following form. So we say that it can grow, but not too fast. And too fast, we have here this n factorial speed. So this, it can grow fast enough, as we can see. And we prove that such formula, the expectation for exponent of integral of logarithm 1 minus u of x eta dx is equal. So we represent this expectation of exponent as a series, and from 1 to infinity, minus 1 to the power n factorial. And here we wrote the integral to the power n, u of x1, u of xn, and here the factorial moment measures of the process eta, dx1, dxn. So under such condition, this E-series converges absolutely. So we just use this condition to prove that we can write this. And this was true for a function u that is this is true for function u, true for u that is bounded by some constant a, where a is less than 1 over c, this one. Okay, so this was done. So how we will use this to prove that we have the equality by the distribution of 2-point processes. So here we will use criteria that we proved on the second lecture, that 2-point processes are equal if their Laplace transform are equal for non-negative functions. So now let's formulate the proposition, and then we will prove it. So assume that we have 2-point processes, eta and eta prime be point processes. On x with the same factorial moment measures. Let it be alpha n. So we have this quantity for all powers. So now let us assume that we have a sequence of subsets pk such that they increase to all space x. Pn increase to all space x. So we can, you can imagine the sequence of increasing balls in the RZ, and we have numbers ck that are non-negative. We have numbers such that. So I will write almost the same assumption from the previous statement, that n's factorial moment on this subset grows not faster than Kn. So here we see that we can have different constant C for each subset, but the speed of the growth is the same. So this is the main difference from the previous one. So then under this condition, we will have that eta is equal to eta prime by distribution. So just have the uniqueness of point processes. If we know this. Okay, so almost all we already proved. So let's see how we can what we should do here. So as I said, we need to prove is enough to prove that Laplace transform, denoted by L, eta of V is equal Laplace transform of eta prime of V for so here you consider V is a function from x to r plus. So this is non-negative. We have this unbounded, non-negative function. But in our case, we can consider only those who which non is zero on each on some subset Bk, and b of x is 0 for x in some set b where b one of this subset. So this means that if we prove it for all such functions, then we can use monotonic convergence theorem to get this equality for arbitrary non-negative bounded functions, because we then use monotonic theorem, and we know that Bn converges to all space S. So we use this. So let's take such a function V and assume that since it is a bounded function, let A be its upper bound, so that supremum of B is less than A. So now let us apply previous formula. Apply, let me not denote it as star. So this one, apply this one to the function. So what is a Laplace transform? This is just expectation of the exponent or integral of this function. But in the formula star, we have the logarithm 1 minus. So what should we write? What should we take? We should take the function u for u of the form 1 exponent 1 minus e to the power minus tv. Let us choose this constant tv a little bit later. So let us see that for such a function we will have Laplace transform. Indeed, on the left-hand side of the star, we have that here exponent integral logarithm 1 minus u eta dx. So if I substitute, you can see easily that we will have just exponent, I don't know, exponent of the integral of minus TV. So this is just by the definition, you can recall it for the Laplace transform of this function, of the function of the process eta function t. So since we want to apply star for this function u, we need to check these assumptions. And the first assumption was that u is less than 1 over c, where c is taken here. So, and we can do this choosing this constant t. So what form of this t? So I want that u is less than 1 over c. Let's the c, this is such c. Let me take right here that this c corresponds to this subset b. B is constant c from this. So we have for each subset bk, we have its own constant ck, but I choose some b and I denote this ck by c. Okay. So when it is true, you can easily see that this is true for t is less than minus 1 over a. This is the supreme is a bound for function b, and here logarithm 1 minus 1 over c. So this is just simple inequality, and for such t we can use now the formula star, because assumption with speed of growth satisfied. So we have for such t, so for t in 0, and this one minus a logarithm 1 over c. Here we can assume that c is bigger than 1. Okay. So it is less than is non-negative. Okay, so for such t, using the formula, we can see that Laplace transform of tv is equal Laplace transform of eta prime tv. Why is it so? Because we can apply the formula star, and this formula, the right-hand side of this formula, uses only factorial moments measures of the point process. So if we know that series converges absolutely, then and this measures are equal, then we have the same left-hand side. So the Laplace transforms are equal for this measures eta and eta prime. Okay, so we can see that this is true for such t, and but we want to take t is equal to 1. T is equal to 1. Again, we take it, and yes, it can seem that actually this Laplace transform, if you let us recall it of tv, this is just expectation exponent minus integral tv of x eta dx. So actually this function as function with respect to t. So if I take t and consider this Laplace transform, you can see that this is analytic function. Analytics TV is analytic function. So if this means that if we have the equality on some interval for analytic function, this will give us that we have equality of these functions for every t, for t is from 0 to infinity. And this means that we can take t is equal to 1. So for t is equal to 1, we get that Laplace transform of eta is equal to Laplace transform of eta prime. And this proves the state. So here what we done, we just find the condition on factorial moments, or for factorial moments measures that, and we see that if they grows not so fast, then we have uniqueness by the distribution of two processes. So we can apply this. So if we know that for some two processes, we can see that their factorial moments measures are equal, then this means that this is the same process, because in many cases we construct the point processes in some different ways, but we need to understand that we have the same processes. So this can help us. Okay, so let's move forward, and as I mentioned on the beginning, I want to show the generalization of Mecke equation for multidimensional case. So this will be Mecke equation. So let me recall what it was for one-dimensional form. So it was true only for a Poisson point process. So for a Poisson point process, we have the characterization of this point process, and we say that if I have a Poisson point process with intensity measure. Now then, if I take a function f that acts from the space x times a space of moments of measures 2r. So this means that my function depends on a point and on the measure itself. Then if I integrate over all points in the point process eta, x and take the expectation, then this is the same if, so I take the expectation, took it under the integral, and I write this to this process eta, I should add the point x itself. So this means that I add to the point additional, I add to the point process additional or fixed point x. So here x is fixed, so you take the expectation with this randomness, and then we integrate over space x with respect to intensity measure lambda. So here you take the expectation over all such integrals, but here just the expectation is taken over this randomness. So we can generalize this formula for multiple case. So what is it? So I take here just a function that depends on one point, but we can consider a function that case, multiple case. So here now will be fx from x to the power m times space of measures to r. And again, the question is how I can find the mean value of such integrals f from x1. Let me write the variable of integration y. Do not miss it with random points later. So x m, and here instead of just usual point process by itself, I write its m's factorial power dy1 dy. So this is a generalization, and the answer will be almost the same, but not. So we should add to the point process additional of this m points. So I write here y1, so ym, and add to the point process eta this additional points m, and integrate with usual power of intensity measure dy1 from dy. So this is the Mecke equation. And again, as on the beginning, this is true only for Poisson point process. So this is very important that this formula, so one-dimensional case, actually, so we have that if we have this formula for every function f, then we have the inverse statement that this is, if we have this equation equality, then we can guarantee that eta is a Poisson point process. So we proved it on the lecture 5, I believe. So if this is true, then the eta is a Poisson point process. So here this equation is true only for one class of point processes, and sometimes it's a great interest to get similar equality for bigger class of point processes. So we need to understand how we can write such form of functionals of point processes. So let's see how to prove this, and I believe next time it will be good to consider some examples how we can use this formula. So, but now let us try to prove this. So actually the proof is similar to the one-dimensional case. So for those who can recall that proof, it will be not hard. So we will take the first step and the main one step that we consider. We assume that intensity measure of the Poisson point process of all space is finite. So under this condition, we constructed a Poisson point process as sum of random number of delta measures at random points. So how we did this? We write this Poisson point process in terms of this xi, I from 1 to kappa, where here xi independent identical distributed with probability measure on x, and kappa has Poisson distribution with parameter gamma. And here what we have, and this measure lambda can be given as the product gamma times Q. So we prove this. If we have, in this case, if we consider this one, then intensity measure of such point process is this one. So under such condition, you can find the probability measure and this constant that will actually this is equal to lambda of x. Okay, so in this case, we can write the left-hand side of the equation. I denote it by 2 stars. This is 2 stars. So let's write left-hand side. So I have the expectation of integral of a function. I will write y to not mix them up, and factorial power of ty. And so we recall that this is, let me write once more. So the integral with respect to factorial measure, this is the sum over non-equal indices, and they should be less than this random variable kappa. And here I write this random points xi1 and so on xim, and instead of measure eta here, I write delta measures, the sum of delta measures, 1 plus and so on plus delta x kappa. So what was the idea previous time is to take all possible values of this Poisson random variable. So it can be, as I told, we have non-zero value here, only for k which is not less than m. So we can take value of k from m to infinity. So I write this. This is k from m to infinity. So that this is all possible values of random variable kappa for which this sum is not equal to 0. Then the probability that, and here, very important, then we have that kappa is independent of these random variables. This is important. So here I use independency, and I can write the probability of this event that kappa is equal to k, and this is equal to e to the power minus gamma, gamma to the power k, k factorial. So here I just write the same, not less than k, and the same as I am. And here now I know the exact number of summands here, x1 plus delta of x k. This is k. So, and I forgot somewhere expectation. Well, I can write expectation here, but since I have the finite number of summands here, so I write the expectation here. Okay. And now I will split this, write this expectation. So I know that x's, xi's are independent, identical distributed, and have the probability measure q. So here I want to first to take the expectation with those points which are present here. And also know that that the answer is the same, or if I change the points, because they all have the same distribution. And here I can change summands as well as I want. So to write this expectation, I will, let me write for one of the summand xim delta x1 plus delta xk. Let me take, for example, x first, x2, and so on. So it will be x2 and so on, xn. So what I will write this as expectation. So I will integrate over first indices here. So I'll write here y. So I denote them by y. So let's place x m. And here I just write first delta measures with indices y, m, and others I leave by itself, or I from 1 to k minus m delta x I. So since they are all have the same distribution, it doesn't matter what index I put here for expectation, it doesn't matter. So I integrate with first independent random variables, so I use just the product of their distribution, dy. So this we have for one summand, and they are all equal. So let us calculate how much we have of them. So since how much summons do we have? So we need to choose m points among k. So if I choose m points among k, I have k factorial over m factorial k minus m. And since they are all the same, so the answer does not depend on the order. So we add all them together. So we multiply by m factorial as well. So we have this amount of summons that I substitute here. So let me continue. I continue here. So what do I have? E to the power minus gamma here, sum from m to infinity. And here I have this summand as well, k factorial. It will disappear. So I will have only k. Okay, let me write over k over k factorial. And this one, what we have, k factorial. This one disappears, k minus 1 factorial. This will disappear too. And I just write this. I can change the order of integration here. Since I have non-random integral here, and function f is bounded. Oh, not. I forgot to say that we consider f is non-negative. R plus non-negative function. So if we have non-negative function, we can change the order of integration and expectation. So we have here the expectation f over y delta plus and so on, delta y m, and here plus 1 to k minus m delta x q m dy. So here the last step, what you can see the formula which we use when we write down all possible values of number of summands in a Poisson point process. So I do the reverse step. Let me write here to understand k minus 1, and here I write gamma to the power m. And I can change the summation now, not from k equal to m, but just from k is equal to 0 to infinity. And I have gamma to the power k factorial. So I just did them change of variable, and here expectation f from y and delta y first and so on, delta y m plus from 1 to k delta x. So here I just make the change of variable of this of k to the power n t1. So now put them together, this gamma to the power m and q to the power m. I will have the integral with respect to, let us recall, we have this one, lambda is equal to gamma times q, and I can write this is just the this is written than just the form for a random number of summands for this one. So I can put this all together and write the expectation f from y tilde y first plus tilde ym plus, so I write here the Poisson process eta. I can write so, and put them together here, lambda to the power m t1. So this is what we done. So we proved this formula, and the idea of proof was the same. We just here have slightly bigger number of variables and summands, but the idea is the same as for one-dimensional Mecke equation. And here the important thing that we use here the property that the points in the process, in the point process, are independent here, independent, and we have not a Poisson number of summands. So this actually here the part where the distribution of the number of summands plays role. So we cannot do this for arbitrary point process, but only for a Poisson point process. So next time we will see how we can apply these formulas, one-dimensional and multi-dimensional equation for a Poisson process and for all. And here I forgot to say that second step to when we consider that lambda is equal to infinity, but I believe one time we did such a step from the previous one, so we just need to consider the sum of independent Poisson processes. We did it once, so I left it because we considered the main idea here. And for today, this is all. If you have some questions, you can ask. Okay, if no, then thank you.